So the next speaker is coming from Durham University, is Dr. Dario Tessicini, and is going to talk to us about questioning Copernicus, cosmological principles on the eve of the scientific revolution.
Hello, hi. Good morning, everybody. Thanks for coming so many on a cold Saturday morning. I'm going to turn the clock back by around 500 years, going back to the beginning or even the prehistory of the so-called scientific revolution. I hope my talk is not too disconnected from the rest of the day, because I think it's the only one that deals with topics that go so much back in time. I hope to show that some of the concepts or issues that affect contemporary science, controversies, the use of diagrams and visual illustration, also come back with Copernicus and the early Copernican. So, without further ado, look at what I will try to do is to look at some of the continuities between Copernicus and the tradition that preceded him, and also the consequences of the Copernican theory of the celestial physics. Some of these consequences are intrinsic to the heliocentrism, although not all of them were foreseen by Copernicus himself, and some were not only unforeseen, but also in many ways undesirable for Copernicus. There are some common notions and assumptions about Copernicus that I feel we need to go through again very quickly. What we know about Copernicus is that after a period of training in Italy between the end of the 15th century and the early years of the 16th century, Copernicus worked mostly on his own, mostly isolated by the scientific community of the time. This is at least the common perception. It holds, for the most part, we know that Copernicus had contacts, exchanged letters with other astronomers, astrologers, and the very fact that the Revolutionibus was dedicated to the Pope means that there were contacts between Copernicus and Rome before the publication of his work. You just don't, at the time, you just don't dedicate your work to the Pope in the same way in which we don't send gifts to kings and queens for no reason at all. Secondly, heliocentrism is based on a small number of observations. And we know that Copernicus mostly relied on Ptolemaic astronomical data. Copernicus did a few observations, in fact. He did all the observations he needed to predict planetary positions. In the De Revolutionibus, the last observation recorded by Copernicus is 1529, an observation of Venus. The third notion we have of Copernicus is that his astronomical models have more or less the same explicatory power of the Ptolemaic ones. They explain the same phenomena, although it can be argued that they are slightly simpler than Ptolemaic astronomical models, and they don't use some physically awkward models, the equants. Copernicus' program was to, as I will show, was to reconcile the astronomical models with the celestial physics. And we are going to see how he did it. So before looking at Copernicus, I just want to give you some directions on what was the cosmos at the time of Copernicus. That is the geocentric cosmos. there were some principles that were common to both the geocentric tradition and Copernicus. The universe is spherical and therefore finite. This is a metaphysical necessity of the Aristotelian thought. The motions within the universe are circular and uniform, where uniformity means that all planets have the same linear speed. Therefore, the order of the planets can be established according to the observable periods of the planets themselves. So slower periods of revolution means that the planets orbit around greater circles, and therefore they need to be to a greater distance from Earth. At least this is in theory. As you can see from this diagram, Mercury, Venus, and the Sun all orbit around Earth in 1 year. This is because in a geocentric system, it's Venus and Mercury appear to orbit very close to the Sun. Actually, it's very difficult to observe them, and therefore the geocentric system did not manage to compute the orbits of Venus and Mercury. However, geocentric astronomers and natural philosophers argued that Mercury and Venus were below the Sun on the basis of philosophical arguments that were, however, a point of controversy and were considered to be, they did not solve the issue at all. The diagram that you see here is from 1519, so we are just before Copernicus' publication of the Revolutionibus and during Copernicus' lifetime. I'll show you this diagram because geocentric diagrams at this stage usually don't indicate periods of revolutions within the diagram. I've looked at quite a few of them and only found that 2 of them have the periods of revolutions in the diagram. The one that I just showed you and this one, which comes from a cosmographical work published in 1588 in Italy, where also it says that Mercury turns around the zodiac in the same time as the Sun, and the same goes for Venus. Now, if we look at Copernicus' De Revolutionibus in comparison with Ptolemy's Almagest, we see that De Revolutionibus is modeled almost exactly on the Almagest. It means that Copernicus' idea of his discipline, the order of the topics is just like Ptolemy. Ptolemy was Copernicus' model. You can see that there are only slight variations in the structure of the 2 books. If we get even closer to the text of Copernicus, we see that the influence of the Ptolemaic tradition is even greater. This is a comparison between chapter 10, book 1 of Copernicus. This is the chapter where Copernicus presents his own heliocentric system. This is where we find the famous diagram that we will see in a minute. On the right-hand side, there is a translation of a chapter from the Epitome in Almagestum. The Epitome in Almagestum is, as defined by Noel Swerdlow, the finest textbook of Ptolemaic astronomy ever written. The Epitome is truly the peak of the encounter between Renaissance science and humanism. It originates from a manuscript of the Almagest that arrived in Europe with Cardinal Bessarion in the mid-15th century. Bessarion gave the manuscript to the best astronomer of the time, called Feuerbach, who also made a new studies on planetary movements. And the result of Feuerbach's work and of his pupil Regiomontanus is the Epitoma, which is a textbook in which not only the content of Ptolemy's Almagest is summarized, but it's also studied in relation with the knowledge of the time. So it's a sort of summa of Ptolemaic astronomy at the end of the 15th century. This is a very influential book for Copernicus that gave him a precise understanding of Ptolemaic astronomy. From the Epitoma, Copernicus also took some of the astronomical or the geometrical devices that he uses in the Revolutionibus. We see in this passage, so in this crucial chapter for Copernicus, how he organizes the chapter by basically rephrasing Regiomontanus. So he begins by dealing with the order of the planets as known to the ancients. Then he presents his own principle for the order of the planets, which is the period-distance relationship. Their principle of the ancients assumes that of objects moving equally fast, those farther away seems to travel more slowly, as is proved in Euclid's optics. It is significant here that Copernicus refers this the principle of his own astronomy not to Aristotle or to the philosophical tradition, but to Euclid. So what Copernicus does, he transforms what was a metaphysical principle into a geometrical one. Then he talks about Venus and Mercury. And here he takes the lead from Regiomontanus, which says there was controversy on the remaining three, controversia fuit. That is, in Ptolemaic astronomy, it's not possible to decide whether Mercury and Venus are below or above the Sun. And this is the point from where Copernicus, in a way, begins in his investigation. This is what Copernicus thinks is also his main achievement. That is, heliocentrism sets the record straight, and by converting the geocentric astronomical devices into heliocentric device, it is possible to order the planets according to their periods. He continues, Copernicus, I was impelled to consider a different system for no other reason than the realization that astronomers do not agree among themselves. So I look quickly at Copernicus' transformations of geocentric models into a heliocentric one. He does a very simple substitution. That is, once the annual motion is attributed to the Earth, all the annual motions that were attributed to the other planets are eliminated. So in this way, and here we have the Sun at the center of the planetary motion, in this way, Mercury and Venus only need a deferent to orbit around the Sun. There will be a smaller deferent for Mercury, a slightly larger deferent for Venus, and then the order that comes out of it is basically this one that we see in the Revolutionibus, where Mercury and Venus are order univocally below the sun, below the Earth at this point, and closer to the sun, and the Earth takes the position of the sun. It's interesting how Copernicus talks about his own achievement. In this ordering, we find that the world has a wonderful commensurability. He uses the term symmetria, and that there is a sure bond of harmony for the movement and magnitude of the orbital circles, such as cannot be found in any other way. Here we are again in the first book of the Revolutionibus, which is the cosmological book. But the issue returns also in the fifth book, which is the book dedicated to the study of the planetary orbits. And again, you can read the text. The mobility of the Earth binds together the order and magnitude of the orbital circles in a wonderful harmony and sure commensurability. So the Copernican advantage over geocentrism is the possibility of having a planetary order coherent with the period-distance relation, which for Copernicus, again, is rooted in geometry rather than metaphysics. He thought that heliocentrism, by sacrificing the Earth's centrality and immobility, reconciled physics and astronomy, since the sun's central position allowed for a planetary arrangement that was coherent with the principle that celestial motions are circular and all have equal linear speed. So, to sum up the contribution that De Revolutionibus did to 16th century astronomy, that is from a 16th century point of view, it orders the planets by their periods, eliminates non-uniform motions that were introduced by Arab astronomers, explains the occurrence of retrograde motions when planets and when the planet is in opposition to the sun, and attributes diurnal motion to Earth and not to the sphere of the fixed stars. There are also some open problems that will be investigated by the next generation of astronomers and natural philosophers. First of all, Copernicus introduced a third motion to the Earth that is unnecessary. This will be found out pretty soon after Copernicus' death. There is then a question on the size of universe required by the heliocentric universe. This is also a problem that will be quickly picked up by the early Copernicans, and a source of much controversy at the end of the 16th century and then going to the 17th century. Also, heliocentrism introduces multiple centers of motion. The Earth is in itself a center of motion as it carries with it the moon. The concept of, this concept was kind of awkward, or very awkward for 16th century astronomers and philosophers. The concept of satellite will be introduced much later by Kepler, and we will see at the end of the talk how Galileo's discoveries will help to support the Copernican arguments. And above all, the main problem of the heliocentric of the Revolutionibus was that Copernicus says almost nothing about the causes of planetary motion. So Copernicus does not explain how the planets or why the planets move in that way. He only explains the hows. And this is something that will basically motivate Kepler's research at the end of the 16th century. Now, talking about Kepler and the early Copernicans. Now, I will just flag up a few themes that come out after the publication of the Revolutionibus. This is a period of the history of science, the period between Copernicus and Galileo, which tends to be slightly overlooked. That there is a sense sometimes that the Revolutionibus was not widely read, which is not true, and that there were not that many Copernicans before Galilei, which is only partly true. There were about, we know of at least 10 authors, 10 astronomers or natural philosophers that supported a physical interpretation of heliocentrism. And some of them are quite important for the development of astronomy and cosmology in the 16th and the 17th century. This diagram, for instance, is not really widely known. It's a diagram that was published as an appendix to Kepler Mysterium Cosmographicum, Kepler's first work, and it was produced by Kepler's teacher, Michael Mestlin, another Copernican, a professor of astronomy, and it's a diagram whose intention is to interpret a Copernicus diagram. It was simply meant as a sort of reproduction of Copernicus, but as you can see, there are some characteristics that already depart from Copernicus. First of all, is the size of the sphere of the fixed stars. The attribution of diurnal motion to Earth means that the fixed stars do not need to be transported all together by one sphere, which also coincided with the outer boundary of the universe. And here in this diagram, we see for the first time how the sphere of the fixed stars acquires a sort of, depth. Even more interesting is the space between Saturn and the Sphaera Stellarum Fixarum. This is also a consequence of the Copernican heliocentric theory, something which Copernicus was aware of, but he decided not to put this information into the diagram. And this has to do with the space between Saturn and the fixed stars, which Mestlin calls an interstice between Saturn and the fixed stars, which is immense or infinitesimile, or almost infinite. So the concept of infinite is extremely controversial at this point, and it's interesting that it appears here for the first time. When we look at how Copernicus was interpreted in the 16th century, we see that this possibility to extend the geocentric cosmos, to extend the cosmos way beyond the sites of geocentrics, returns in the early interpreters of Copernicus. Here we have the English natural philosopher and mathematical practitioner Thomas Digges, who writes a pamphlet called A Perfect Description of the Celestial Orbs. We are 30 years after Copernicus, and for the first time we see the fixed stars expanding freely in the universe. It might seem that this extension is unbounded. When we look more closely at the text, we see that there are some limitations in Digges' ideas. He talks about the sphere of the fixed stars in theological terms, as the habitacle of the elect, which was an expression used to mean basically paradise or God's abode. The other question is that if the universe is infinite, then it cannot have a center, while here in this diagram we see that the universe is still centered on the sun. But it certainly, with Diggs, there is a step forward in the interpretation of heliocentrism, of the possibility of heliocentrism towards infinities. And again, when we proceed further, we find Giordano Bruno, a natural philosopher that threads the fine line between unfaithfulness to Copernicus and mere misunderstanding of the intricacies of mathematical astronomy. Anyway, Bruno writes a series of scientific dialogues in London, supports the idea that the universe is physically infinite. Bruno's infinity is based on a metaphysical necessity, according to which God's potentia absoluta, God's potency cannot have any limit, and therefore also the creature has to be unlimited. So the universe is physically infinite, and he thinks that in the same way in which the Earth is one of the planets, also the Sun is one of the stars, and this infinite universe is populated by an infinity of solar systems that are analogous to our own. There is one interesting idea from Bruno about harmony and commensurability. Bruno thinks that in an infinite universe, it is not possible to conceive a sort of harmony like the one conceived by Copernicus. So in an infinite universe, there is no geometrical harmony that runs through the entire universe. If there is harmony based on the self-sustainability of the whole system of infinite planets. Also, Bruno, on the same grounds, thinks that planets do not have to move necessarily by uniform circular motions. And in fact, he thinks that planets move according to spiral motions. By spiral motion, he intends some sort of cycloids that bring the planets around the sun, around their own sun, but always in different, never going back to the same place where they were before. In some way, Kepler, certainly the most skilled astronomer of his generation, shared with Bruno the same preoccupation for finding the reasons of planetary motions. However, he remains bound to the idea of the Copernican harmony. That is, that the universe needs to be explained through harmony and proportion. Harmony and proportion that he finds in the 5 Platonic polyhedra, then another idea that comes from ancient times, and that for Kepler explain the number, the size, and the distances of the planets. Of course, in trying to explain Copernicus, Kepler finds out that the planets do not move according to circular motions, but move in elliptical orbit. So an idea that was alien to Copernicus. I'm going towards the conclusion. Just before, of course, the main era of the scientific revolution of this time is Galileo and his telescopic discoveries that seem to confirm heliocentrism. The moon, as we know, is similar to the Earth. Jupiter has satellites, and above all, Galileo discovers the phases of Venus. The phases of Venus are basically the death note of Ptolemy. Once Galileo discovers that the Venus has complete phases, that's the end of geocentrism. But there is one aspect that I think it's worth to think about, which is Galileo does not simply point the telescope to the heavens. He invests greatly in improving the technology and also in understanding what he sees. Galileo was not the first one to point the telescope to the moon. He was preceded by the English Thomas Harriot, who produced this drawing in a few months before Galileo. But Harriot has difficulty in understanding what he sees. He has more or less the same data as Galileo, but he hasn't got the same training in translating the data, that is in draftsmanship. So Galileo, after a few months, Galileo observes the moon and he interprets the moon spots in terrestrial terms. So interprets them as the shadows on the sun over valleys and rough landscape. What happens then is that Harriot gets Galileo's Sidereus Nuncius and he redrafts his own drawings. And what he does, rather than looking at the data again, he imitates Galileo's data, even though he does not really acknowledge it. And we know this because you can see that Galileo slightly exaggerates the size of the crater of the moon. And Harriot does exactly the same, which means that Harriot was not looking at the moon at that point, he was looking at Galileo's drawings of the moon. So what he does, the way in which this data, Galileo knew that, you need to understand the data. These are not just simply raw data that you write down. Last point to conclude this short, very partial history of early modern cosmology. The issue of harmony and proportion, we know it's something that has a long history and that informs research programs from antiquity perhaps to the modern age. We know, however, that the word cosmology was not used until the mid-18th century. Here we find in the entry of Diderot's Encyclopédie the first definition of cosmology as a discipline that sends readers back to Christian Wolff's Cosmologia Generalis, which is one of the great works of the German Enlightenment. This is what is usually regarded as the beginning of modern cosmology, which is only partially true because already in the 16th century, even the word cosmology existed, even though it was not really current. Here we see it on the Cosmologia is the title for a pamphlet or a short work by a French physician and astrologer called Antoine Mizot, where Cosmologia is the description of the world, of the heavens and of the earth, what we now call maybe cosmography or cosmographia. I think I'll end here. Thanks.
So that was wonderful exposition of the importance of words and drawings and copying drawings and understanding science. Okay, so we have time, 15 minutes again for questions and answers. Over there.
thanks for the great talk. There was a lot of talk about the conflict you have between the scholastics earlier on and Copernicus, Galileo, the people who followed. I know it's a bit of a, sorry, hear me?
Yeah.
Yeah, cool, sorry. I know it's a bit of a guessing game, but if that scholasticism hadn't been there, if the story had been different and we hadn't had that very rigid academic tradition already in place, do you think it would have been easier or harder for Copernicus to have come? Because he's already taking these ideas of, like classical ideas from Euclid. Do you think it made it harder that there was that pressure back?
Well, to a large extent, Copernicus is the product of medieval scholasticism that he encountered and studied within that system in Krakow and then substantially in Italy. Sometimes when we look at the history of the details of the history of science, we see that we see that there are continuities. So in some way, what Copernicus was trying to achieve was to align the principles of philosophy, of natural philosophy, with the practice of astronomy, in order to, his intention was not really to go counter Aristotle or the science of his own time. Of course he did, and he was aware he was doing it, but the principle, and this is what perhaps was one of the points I was trying to raise, that the idea that the order of the planets had to be to conform to the period distance relationship is something that he learns through the works of the ancients, but also mediated by medieval scholasticism. I don't know if that answered your...
Thank you very much.
So it's very difficult to see whether it was easier or it just, this is how it happened. So I don't think we have it. I can't say whether if...
Thank you for an interesting review of some fairly old history, but it always comes up with some new points. I was particularly interested to see your quote from Copernicus saying that I was impelled to consider a different system for no other reason than the realization that astronomers do not agree amongst themselves. So I suppose you could say that had there been a consensus amongst the astronomers of the time, then Copernicus's revolution would not have happened. Could you comment on that?
Yes, in theory that could have been the case, because if what Copernicus is referring to exactly at that point is the disagreement between the use of a homocentric system, a system that involves eccentrics and epicycles. But he says, and I think there is some evidence to say that this is actually genuine, this is what he means, that his research started because he felt that there was a crisis in astronomy. A crisis that was produced by several different aspects of geocentric astronomy that did not work. And so he wanted to, so to say, to set it right. I have highlighted in particular the period distance relation because, especially in the more recent literature on Copernicus, that has been an aspect that has been underlined by recent historians. But of course, there were quite a few things that made Copernicus and other astronomers unsatisfied with the status of astronomy at the time.
Hello. Thank you for a fascinating tour, historically. I recall that Giordano Bruno was executed. On that rather sour note, and I remember learning about this from Carl Sagan, actually, the actual political, ecclesiastical political climate at the time how much do you think that was at the back of these minds in the way that they were not only presenting but also conceptualizing?
Well,
Thank you.
the situation is very different at the time of Copernicus, at the time of Bruno, and at the time of Galileo. So there are quite dramatic historical changes. Copernicus lives right at the time of the Reformation. So when he goes study in Italy at the beginning of the 16th century. 20 years later, or maybe 30 years later, students from that part of Europe could go to Wittenberg. In fact, the publication of the Revolutionibus is kind of affected already by this controversy between Reform and Catholic. And so for Copernicus, the political or religious situation affects the publication of the Revolutionibus, which is dedicated to the Pope, but has a prefatory letter by an important Reformed theologian. For Bruno, it's another completely different situation. Anyway, Bruno was not executed for his cosmological ideas. Bruno wrote works that had more nefarious consequences. He wrote works that were interpreted by Catholic theologians as offensive for the Pope, and so there was a very complicated trial that lasted for 8 years, of which his natural philosophical ideas was a part, but perhaps not the main part. And of course, Galileo is a completely different story, which also has different political implications. So I think all these episodes need to be seen in their own context, and then, also in their development.
My understanding is that Copernicus was much influenced by Hermetic philosophy, and it's an influence you still find in Bruno and you still find in Newton. The notion that the ancients knew all of this and the knowledge has been lost, and we're rediscovering it.
This was a philosophical interpretation of the beginning of the scientific revolution that was very popular perhaps 20 or 30 years ago by the books of Yates on Bruno and the Hermetic tradition. And now, this is also a source of very recent controversy among scholars of Copernicus. I can mention at least 2 very recent books that look at Copernicus from the point of view of Platonic philosophy. And there are at least 2 other books that look at Copernicus as a product of Aristotelianism. I mean, my own interpretation is more towards the second than the first one, as probably has emerged from my talk. The question of Hermetic or magic ideas, I think it has been, at the time, I think it has been surpassed. So, although I think that Francis Yates wrote an extremely, a wonderful book, a very influential one, I think that paradigm has been truly revised. So it's difficult to see. It is true that Copernicus talked about the sun as a sort of divinity in the middle of the planets, but you could do the same in the geocentric system, because in the geocentric system, the sun is at the center of the planets. There are 3 planets below and 3 planets above.
Doesn't he specifically mention Hermes Trismegistus as a symbol for the sun?
Copernicus, well, there are some references, yes, that can be referred directly to Neoplatonic philosophy and narratives.
The time between Copernicus and Kepler is, I think, about 100 years.
The time?
The time between Copernicus and Kepler is, I think, about approximately 100 years. It's a pretty long period. And during that period, it was not only that the theoretical science, the astronomy developed, but also the empirical science, the experimental science there were more measurements on the movement of the planets made by Tycho Brahe in Prague, and that pushed the science forward. I think Copernicus could not have made the conclusion that the planets moved in elliptical orbits because he did not have the data. Kepler already had the data. It was acquired by Tycho Brahe.
Yes, I completely agree with that. Yes.
Thank you.
Yes.
So with this agreement, we move on.